You're listening to Astronomy Daily. I'm Anna.
And I'm Avery. It is Saturday, the 7th of March, 2026, and as usual, we have a packed show for you today.
We absolutely do. Here's a question to get you thinking. Back in September 2022, NASA slammed a spacecraft into an asteroid. You probably remember that. But did you know that we only just confirmed something remarkable? That impact didn't just nudge the asteroid, it actually changed the orbit of an entire asteroid system around the sun.
For the first time in human history, we moved the celestial body's solar orbit. And that's just story one. We've also got gravitational waves, a spacecraft emergency in orbit, a 45-year-old theory biting the dust, our young sun blowing its very first cosmic bubble, and a gorgeous double planet show in tonight's sky. Let's go.
So let's kick off with the DART story. And I think it deserves a moment to really sink in. We already knew that DART was a success. We knew it shortened the orbit of Dimorphos around its partner asteroid Didymos by about 33 minutes. That was confirmed back in 2022. But a new study published yesterday in the journal Science Advances has revealed something even bigger.
Right, because Didymos and Dimorphos are gravitationally linked. They move together. And researchers have now confirmed that the debris blasted off Dimorphos during that impact was so enormous, we're talking over 1 million kilograms of rock and dust, that it gave the whole binary system an extra kick.
And that extra kick was measurable. The orbital period of the entire Didymos system around the sun shortened by 0.15 seconds. Now, I know that sounds tiny, but this is the first time a human-made object has measurably changed the path of a celestial body around our star.
To even measure that, the team had to get incredibly creative. They tracked what are called stellar occultations, moments when the asteroid passes in front of a background star and briefly blocks its light. Volunteers around the world contributed 22 of these observations between October 2022 and March 2025. 22 pinpoint moments of a star blinking out. And from those, they derived a change of 0.15 seconds in a 770-day solar orbit.
The momentum enhancement factor turned out to be about 2, meaning the debris ejected by the impact roughly doubled the total push given to the asteroid. DART didn't just hit Dimorphos, it turned Dimorphos into a rocket.
And Thomas Statler, lead scientist for Solar System Small Bodies at NASA headquarters, framed it perfectly. He said, a tiny change can, given enough time, grow into a significant deflection. This result validates kinetic impact as a genuine planetary defense technique, not just for nudging a moon, but for altering the path of an entire binary system around the sun.
ESA's Hera spacecraft, which launched in 2024, is expected to arrive at the Didymos system later this year to study the aftermath up close. So the science from this impact is very much still unfolding.
Story 2, and it is a landmark one. The LIGO-Virgo-Kagra collaboration, the LVK, has just published the 4th edition of the Gravitational Wave Transient Catalog, known as GWTC4. And the headline? They've more than doubled the total number of gravitational wave detections ever made.
Before this release, the entire catalog contained 90 candidates from 3 previous observing runs, stretching back to 2015. This new catalog adds 128 new events, all detected during just the first 9 months of the 4th observing run, between May 2023 and January 2024.
So we've gone from 90 to 218 in one update. And it's not just the quantity that's exciting, it's the variety. The catalog includes the heaviest black hole binary merger ever detected, with each black hole weighing in at around 130 times the mass of our sun.
There's also a binary where both black holes are spinning at roughly 40% the speed of light. And there are 2 new mixed mergers, a black hole colliding with a neutron star. Each one of those is a treasure trove for astrophysics.
Daniel Williams, a researcher at the University of Glasgow and LVK member, put it well. He said they're pushing into new parts of parameter space, seeing things that are more massive, spinning faster, and more astrophysically unusual than anything detected before.
What I love about this is what it means for testing Einstein. The catalog includes an event with one of the loudest gravitational wave signals ever recorded, GW 230814, and the team used it to run precision tests of general relativity. It passed with flying colors, but the fact that we're now running those tests on events this extreme is remarkable.
LIGO and its partners are currently in a maintenance break, but a new 6-month observing run is expected to begin in late 2026. Given how rapidly the catalog is growing, that run could double it again.
All right, story 3, and this one has a genuine element of suspense. Europe's Proba 3 mission is in trouble. ESA confirmed yesterday that they have lost contact with one of the 2 spacecraft that make up the Proba 3 mission.
Let me explain what Proba 3 actually is, because it's a fascinating concept. It launched from India back in December 2024, and it consists of 2 separate spacecraft designed to fly in extraordinarily precise formation, about 150 meters apart, to create artificial solar eclipses in space.
One spacecraft, the occulter, physically blocks the bright face of the sun. The other, the coronagraph, uses that shadow to image the sun's faint outer atmosphere, the corona, without being blinded by the solar disk. And to make this work, the 2 spacecraft must maintain alignment to within millimeter accuracy.
It's an almost absurdly precise operation, and it was working. In May of last year, the spacecraft achieved their landmark formation flying test. In June, they captured the first ever images of an artificial solar eclipse in space. It was a genuine technological first.
And then, on the weekend of February 14th, something went wrong. The coronagraph spacecraft, the one doing the imaging, experienced an anomaly that prevented it from entering safe mode. ESA describes it as a progressive loss of attitude. In other words, the spacecraft slowly lost its orientation.
As it drifted, its solar panels moved away from the sun, the batteries drained, the spacecraft dropped into survival mode, and contact was lost. ESA says root cause is under investigation, and they're exploring whether the companion occulter spacecraft can be maneuvered closer to assist in recovery.
Losing either spacecraft would effectively end the Proba 3 mission. ESA says teams are working hard, and they will provide updates as new information becomes available. This is very much a developing story. We'll keep following it.
Story 4 is a classic example of a long-held scientific belief getting overturned. For 45 years, astronomers thought they understood how stars like our sun change as they age, specifically how their rotation pattern evolved.
The idea was this: our sun rotates differentially. The equator takes about 25 days to complete one full rotation, while the poles take about 35 days. Equator faster, poles slower. That's called solar-type differential rotation. And scientists believed that as stars slowed down over billions of years, they would eventually flip. The poles would start spinning faster than the equator instead.
That flip state was called anti-solar differential rotation. Theoretical simulations predicted it. No one had ever observed it, but the model said it should happen. And for decades, the lack of observations was attributed to limitations in our telescope technology.
But now, researchers at Nagoya University in Japan have used Fugaku, the country's most powerful supercomputer, to run the most detailed simulations ever of stellar interiors. And the result is clear: the flip doesn't happen.
The key was resolution. Previous simulations were low resolution, and magnetic fields faded out of the models entirely. At high resolution, we're talking 5.4 billion grid points per simulated star, the magnetic fields stayed strong. And those magnetic fields, it turns out, are what prevent the rotation from flipping.
Professor Hideyuki Hata, one of the co-authors, said it simply: turbulence and magnetism keep the equator spinning faster than the poles throughout the star's life. The switch doesn't happen because magnetic fields, which previous simulations missed, prevent it.
And there's a bonus finding. Magnetic fields in solar-type stars weaken continuously throughout their lifetime, with no revival in old age. Previous models had predicted a magnetic comeback. That doesn't happen either.
This matters practically too. A corrected model of stellar rotation helps us better understand the sun's 11-year sunspot cycle and could improve our predictions of how magnetic activity affects the habitability of planets orbiting sun-like stars over billions of years.
Story 5, and it's a lovely one, a real window into our own sun's distant past. NASA's Chandra X-ray Observatory has captured the very first image of what's called an astrosphere around a sun-like star.
Our sun has a protective bubble around it called the heliosphere, created by the solar wind streaming outward and carving out a cavity in interstellar space. It's enormous. It extends far beyond the outer planets and shields the solar system from harmful galactic cosmic rays. But we've never been able to photograph it from the outside.
The star Chandra observed is called HD 61005, and it sits about 120 light-years away in the constellation Bitesz. It has roughly the same mass and temperature as our sun, but it's only about 100 million years old. Our sun is around 5 billion years old, so HD 61005 is, cosmically speaking, a baby.
And because it's so young, its stellar wind is dramatically more powerful. It blows about 3 times faster and is 25 times denser than the wind from our sun today. That's why its astrosphere is bright enough to detect in X-rays. The powerful wind collides with the surrounding interstellar dust and gas, and that collision produces X-ray emission that Chandra can detect.
The astrosphere has a diameter roughly 200 times the distance between Earth and the Sun. Carrie Liss of Johns Hopkins University, who led the study, put it beautifully. We've been studying our sun's heliosphere for decades, but we can never see it from the outside. This is the closest thing we have to a photograph of what our own sun's bubble looked like several billion years ago.
The star is also nicknamed the moth because a surrounding disk of dust forms a moth-like structure around it. And interestingly, the dense, dusty environment is actually part of why the astrosphere is so visible here, making HD 61005 a uniquely ideal subject for this kind of observation.
And we'll finish with some skywatching news, because tonight and tomorrow night offer something quite special. Venus and Saturn are meeting up in the evening sky, and it's a treat for anyone who can get outside shortly after sunset.
Venus is already impossible to miss right now. It's shining at magnitude -3.9, which makes it by far the brightest object in the sky after the sun and moon. Tonight and tomorrow, Saturn sits close alongside it, though considerably fainter, at magnitude 1.0.
The best time to look is about 30 minutes after sunset, when Venus will be roughly 7 degrees above the western horizon. Binoculars will help a lot. Saturn should pop into view easily near brilliant Venus. You'll have about 70 minutes before both planets set.
And if you're pointing a telescope at Venus tonight, you're in for an extra treat. The planet is currently showing a 97% lit disk, almost fully illuminated from our perspective. It's a gorgeous sight. Neptune is also lurking nearby, just over a degree from Saturn, though you'll need a telescope to catch that one.
So get outside this evening, if skies are clear. Venus is your guide. Find that brilliant white beacon low in the west, and Saturn will be right there waiting for you.
And that's our show for today. 6 stories from an asteroid nudged around the sun to a planet pairing up into night sky. It's a great time to be paying attention to the universe.
If you enjoyed today's episode, please subscribe wherever you're listening and leave us a rating or review. It genuinely helps the show reach more people.
You can find us at astronomydaily.io for the blog and show notes, and follow us at Astro Daily Pod on all the major social platforms.
Until Monday, keep looking up.
Clear skies, everyone.